This lesson barely touches on the idea of a limit, just enough so that we can understand the definition of a derivative. For a more careful study of calculus, we would really have to dive in and pick apart the idea of limits a little bit more carefully than we will. But for the purposes of our course, what we're going to do with limits just gets us to the definition of a derivative. And so here's a challenge to set up our understanding of what we're about to learn. What I'd like you to do is read this problem and take it on as a challenge. Think about it and pause this screencast long enough so that you can consider this problem. Okay, hopefully you've thought about this and have realized that this challenge is actually fairly difficult. It was a challenge that ancient mathematicians had to consider and had a very difficult time resolving. And as advances in science were being made, the necessity for having a solution to this problem became more and more and more important. And so the race was on to try to find a solution. One possible way that mathematicians explored to get the answer was through the use of secants, because in order to find the slope of this tangent line, or any line, we need 2 points, and in a tangent there's only 1 point, and so therein lies the difficulty. So mathematicians went back to what they knew, and what they knew is they could find the slope of a secant line. Now recall, a secant is a line that passes through an object, so it intersects that object at 2 or more points. And so we've drawn a secant line through the curve, and we've drawn it so that it's fairly close to the slope of the tangent line. So where we've drawn this other point on the curve y equals x squared, is what we've done is we've selected a point that is a little bit further down the x-axis. So we chose arbitrarily, it doesn't really matter, we just randomly chose 1.1. So if x is 1.1, what is y? Well, 1.1 squared is 1.21, so we have this other point. And now that we have the value, we have 2 points on this curve, we connected it with the secant line, we can find the slope of that line. We note that the rise is the difference in the y values, so we get 0.21, and the run is the difference in the x values, which is 0.1. And if we calculate that out, we find a slope of about 2.1. But that's the slope of the secant line and not the tangent line. The challenge is to find the slope of the tangent line. So what else can we do? Well, we find that if we would have chosen a point on the curve that was a little bit closer than our original point, the slope of the secant line actually gets closer to the slope of the tangent line. So for example, instead of moving over to 1.1, what if we would have moved over to 1.01? Well, then that gives us this as the y value, and then we can substitute these values, the change in y over the change in x, to find a new value for the slope. This one's 2.01. Well, again, we've gotten closer to the slope of the tangent line, but we haven't gotten the slope of the tangent line exactly. Now here's an interesting twist. What we can do is, instead of moving to the right a little bit of our desired point, which was x equals 1, what if we move a little bit to the left? All right, let's say we move back to 0.9998. All right, what we can do again is we can find the y value, find the change in the rise over the change in the run, and we get 1.99998. All right, now let's take a look at what we're finding. All right, take a look at this data. We can plot it in this table. So for changing values of x, if we move a little bit to the left, a little bit of right of x equals 1, we can find the slope of the secant lines. Here are the various slopes. As we come closer to 1 from the left, it looks like these numbers are getting closer and closer to 2. As we come from the right, it looks like we get the same phenomena. So what do we think will happen if we get all the way to the tangent line? Well, hopefully we'll be fairly confident that the slope of the tangent line will be 2. And so this is the process that the ancient mathematicians used to find the value of the slope of a tangent line. I think this is absolutely brilliant. But anyway, so let's take a look more formally or more generally at what's going on. What we're doing is we're taking the slope. We're saying here's the old formula, the change in the y's or the change of the x's. If we use function notation, we notice that we put x into the function and then the result that we get out is y. So we use function notation here. So if we put in a number x plus a little bit, h represents just a little bit, x plus a little bit into our function, we'll get a value out. We subtract that with just x at that point. So here are the change in the y's over the change in the x's. All right. And if we simplify this, we get this formula. All right, and this leads us to the definition of a derivative. So when we follow this process, we are creating a function that gives us the slope of the tangent line to any point on the function. So slope is also called gradient. So this is known as the gradient function, derived function, derivative function. Most people just call it the derivative, right? And here it says the derivative function, we read this as f dashed x. I usually call it f prime of x. But as you can see here, as we take the limit of h, the little bit that we move over to the right or to the left of our value, as that number gets closer and closer to 0, we see that this simplifies to a function that will give us the answer for the slope. So let's see this in practice. Okay, so here we go. Let's take this function, x cubed, and we want to come up with another function. The function will tell us the slope of the tangent line at any point to the curve or the graph of x cubed. Now how can we do this? We would use the method of first principles, which means that we use this formula. All right. So, and again, when we look at this formula, it looks very complicated, but it's just sort of a reconfiguring of the slope formula. We're taking the change in the y's over the change in the x's. We just have h here because whenever we do x plus h minus x, the change in the x's, when we simplify that, it always gives us the little h, the little distance that we move to the left or to the right. Anyway, let's go ahead and move in. So what we want to do is, as we move a little bit to the right of our x value, we substitute that into our function. All right. So this is y2, this is y1, and then this already is x2 minus x1. All right. So if we substitute x plus h into our function and we cube it, we get this expansion, and then minus x cubed is the y1. So we expand it all the way out here. We simplify, the x cubes cancel out, so we get something like this. We divide each term by h, or we can factor out h and then divide, and we get something like this. Now, as h gets closer and closer and closer to 0, infinitely close to 0, we'll notice that this becomes closer and closer to 0 as well, and this becomes closer and closer to 0. So as these two pieces basically become 0, all that's left is 3x squared. So as the limit of h approaches 0, basically we get closer and closer to this function, 3x squared. So this is the resulting derivative function. So if we were to take this function and we wanted to know the slope of the tangent line at, say, x equals 1 on this curve, we would substitute 1 in here. 1 squared is 1 times 3 is 3. So 3 would be the slope of the tangent line at x equals 1. What if we wanted x squared? I don't know, I'm sorry, x equals 2. So 2 squared is 4 times 3 is 12. So at x equals 2, the slope of the tangent line will be 12. So this is a function, so the answer is a function that gives the slope of the tangent line. So let's see this one more time. So what if this is our function here? We want to use this formula to derive the derivative function. And what we'll do is we'll substitute x plus h in here for x. So we'll have 2 quantity x plus h squared minus 1. So that goes here. That's y2. And then y1 is our original function. All right. And then the x2 minus x1 always simplifies to h. Now what we need to do is we need to expand and simplify. And then we get something like this. And again, we can cancel out the h's. We get something like this. And again, as h gets infinitely close to 0, this term becomes very, very, very close to 0. And in fact, we believe once we get to 0 that this will become, this will disappear, and so our function will just be 4x. So to find the slope of the tangent line at x equals 1, we just need to, of this function, the slope of the tangent line is going to be 4. And that's going to be it.